Shubham Jani friends, very good morning all of you. The topic was electric flux. We have defined flux and other characteristics also have explained with respect to flux. And one small thing I would like to do today with respect to flux, understanding that expression that we have given yesterday, right? You remember? We said that flux is a dot product of field vector and surface area vector. Of course, we have given the expression as, remember, this phi is E dot times S times cos theta. This is what we have mentioned yesterday. The field intensity, surface area, and most importantly, regarding the theta as well. Theta angle made by field vector with the normal to the surface, not with the surface, we have told. Now, in fact, whenever we write a dot product has a specific meaning actually. So the best way of writing this expression is not simply E times S times cos theta. Rather, I will now write it as this is what E times, yes, I will write it as S cos theta. E times S cos theta is our expression. Remember, whenever we have said A bar dot B bar is equal to AB cos theta, we can write it as A times B cos theta or B times A cos theta. Now, supposing if I write it as A times B cos theta, what is the meaning of that? A means magnitude of A bar. And what is that B cos theta? You remember? B cos theta is not the magnitude of B bar. B cos theta is component magnitude, the component of B bar along A bar. This is what was our definition. Remember? Therefore, now here when we write it as E times S cos theta, what is the meaning? Remember that S bar vector we have always taken normal to the surface. Therefore, now here, this definition, I will write it in a more meaningful form as phi is equal to E times this S cos theta is nothing but S perpendicular. I will make a symbol like this. What is this S perpendicular? So, this is the component of area normal to field. So, normal to the surface means this is S perpendicular is a component of area parallel to E bar, right? This component is S perpendicular is the symbol that I have used. It means that the perpendicular component normal to the surface, or it is a component which is parallel to E bar, right? Now the same expression I would like to show you with the sense of physics. Let me show that small demonstration now. Just look at this demonstration. Yeah, friends, now let us understand this S perpendicular that I have drawn. S perpendicular, as remember, it is parallel component of area with respect to field or a component which is perpendicular to the surface that we have drawn. Now here you see, you will find here a square illuminated with light, right? So this is what is a square area that you observe illuminated with the white light. Now here this whatever slit that I have shown, that square slit, it is now allowing the flux. Here the flux means nothing but the light flux. All that light passing through this square aperture, and what we will see it as here the shadow or the white patch we will find. Now here in this case, theta is equal to 0 degrees. Theta is equal to 0 degrees. Therefore, that S cos theta will be equal to S. S cos theta is nothing but now the complete area of that patch. Now remember, now you see what happens as I change the orientation. Even yesterday we have told orientation of the surface, right? Now you see. Supposing if I start to orient this, then what is the change that you are observing for the case of the patch, you see? Right? Now this was originally the area of the square patch. Now supposing if I am changing the orientation, what is that you observe? Yes, you will see a different shape. Of course, it is also a square, but what you find is that of a lesser area, surface area. As I gradually increase this orientation in the anti-clockwise direction, what you find is that the area becoming smaller and smaller and smaller and smaller and smaller. Now here, there comes, you don't see that square patch at all, where that S cos theta has become 0. Remember, therefore now if this is what is yes, then E bar and S bar are parallel, right? Now this is what is called as S cos theta. This patch that you observe for this orientation for or any other orientation, that is what is S cos theta. Now as S cos theta decreases, naturally flux is also decreasing. That is what is the physical demonstration we should remember. The component of surface area in which direction, right? So this will prove or this will give you a clear picture regarding S cos theta, right? Now let us continue the case of flux. That was all the understanding about flux. Now with that small important concept, here we come to a biggest tool in electrostatics. I have been telling you since yesterday, the Gauze Law. Now let us see first the English part of Gauss Law, and then let us get into the physics part. Now here is the statement. Right. Look at this statement. The flux enclosed by a closed surface. Here few lines, few important parameters. Underline that. Flux enclosed by closed surface is always equal to 1 by epsilon naught times 1 by epsilon naught times net charge enclosed by that surface is the English part. All this complete statement, when shown symbolically, a mathematical expression, we will find this way. Now this is what is phi equal to integral E bar dot ds bar. Now one more time you can answer. Yesterday we have been using that E bar dot s bar. Yes. Remember, in the same class, one more time go back and pause the video and watch it. We said in the case of planar surface, we can straight away write it as E S cos theta. You can write it that way. Whereas in the case of curved surface, you remember that? You remember that where the S bar, the pseudo vector of area, the areal vector, the direction keeps changing, and for that reason we have divided into small elements, large number. Remember that? So for that reason the flux is, so this is how we give a general expression. Phi is equal to integral E bar dot ds bar is, yes, he says 1 by epsilon naught times, this is what I am taking sigma, the summation, right? Sigma qi. Now here in this expression, when I am writing this as sigma qi, remember this is by using the additive property. Whenever we want net charge, this is what is the net charge enclosed by the surface. This qi, when you are writing, I will show those examples as well. That is what we will be using our additive property of the charge. Now this comes all about the English part. And now one more important point when we look at this closed surface. Gauss law is always used for a closed surface is an important thing. When we say closed surface, the geometry is not 1D or 2D, so the geometry is always 3D, right? So closed surface, the geometry is always 3D. So what do we mean by 3D? How it looks like? 3D geometry means it is like, you imagine a spherical geometry or a cuboid geometry, or also you imagine a cylindrical geometry, right? A cylindrical geometry. Now all these things will be definitely symmetric. Now you will put me a question that, sir, does always that closed surface should be a symmetric geometry? Now let us find answers for those such interesting query as well. In fact, this is a law, we said. When we say it is a law, no question of proof actually. When law is stated, it is one of the truth or one of the facts of the nature. Now we cannot say that it is what is the proof of the law. But still on a lighter side, on a very loose method, we will give or we would like to prove this result. Somebody may call this as a proof. Actually, what I mean is, it's nonsensical to say proving a law. Is it? Rather, we will say we are not demonstrating that law. Rather, it will be a better statement from a teacher. So we now demonstrate this result using our known concepts. Remember, we have always been telling that learning whenever it comes, it is always from known to unknown. We never do such abrupt beginning or abrupt endings. Maybe sometimes we will end at a point. Beyond that, maybe not the culture of our PU classes, but never we do that those abrupt beginnings. In fact, here we demonstrate this Gauze Law with our known concept. What is that? Now let me consider a point charge. Okay. This Q, I call it as Q, a single point charge under consideration. This is a point charge, and somewhere over here I consider some point P which is at a distance R. So this is our situation, a point charge and P at a distance R. Now what we do is that we now imagine a closed surface. That closed surface should enclose our charge under consideration. Remember, whenever you come across such closed surface, it is only a imaginary geometry. Never imagine a kind of materialistic edges or materialistic boundary. You never imagine like that. It is a imaginary geometry. Now the question comes, sir, you said a closed surface enclosing the charge. So what shape you would like to take? Okay, in the beginning, let me take it as a spherical symmetry for easier understanding. To begin with, later, of course, let us take any other shape as well. Then we will find what about that. Now, this is what is Q, and point charge, remember, we write electric field lines which are radially outwards. Therefore, here I am now representing those field lines with the green color, right? What is that? Radially outwards. In all directions you will take them, right? In all directions you will write these diverging rays. So arrow marks are always, yes, away from the charge. So whenever it is field line, of course, the most important part is the arrow mark without right. So these are all the field lines. Now, closed surface we need, and as I have told you, for our simple or our convenience, we'll take it as a spherical symmetry. Remember, as I have told you, it is always a 3D geometry, but our board is a plane, is a 2D. Therefore, what we show may appear as a 2D geometry, but it is not 2D geometry. So now what I represent on the board is not a circle. It is not a circle, rather you will see it as a 3D geometry, which is a sphere. So now what we do is that, taking this R, the distance of the point of observation, as radius, now I imagine a sphere. The sphere enclosing the point, the charge of consideration. Yeah. You please take that as a sphere, right? No questions. Don't say it is not appearing as sphere. Yes, it is sphere, right? Okay. Now this is a sphere. And now P is a point. P is a point on this enclosed surface. Now such closed surfaces enclosing the charge, we call them as Gaussian surface. So this will be a terminology which I will be using. So I don't call closed surface around, I will be calling Gaussian surface. Now this is a spherical Gaussian surface. P is a point on the Gaussian surface which is at a distance r. Now these are the field lines. These are all the green color which you have seen. They are all the field lines which are emitting out of the spherical or that sphere, right? That sphere, they are emanating away from the sphere in our direction. Such that, remember, these green lines, they are always normal to the surface at any point. Supposing if this is what is the spherical surface you imagine, this is where E bar, normal surface. At this point it is normal surface. So all these vectors which I am calling it as supposing. Here only I consider the point P. Here only I consider the point P, where I have taken a small element of surface. So this is what I mean by ds bar, element of vector. So whenever it is a case of curved surfaces, yes, the process is divide into large number of small elements. Consider one such element, right? So this is what we did. So this is ds bar, and remember here the field is also because this is a point charge. For a point charge we have given expression for intensity. Remember 1 by 4 pi epsilon naught q by r square. Along with that expression we have told the direction is for a positive charge, it is away from positive charge towards negative charge. Therefore now this consideration, supposing I have given this for positive charge, okay, then this vector in the red color will represent E bar vector, such that you will see that not only at this element of surface, now for any element of surface on the Gaussian surface, you will find that E bar and ds bar are parallel. Is it not? Because anywhere this ds bar is a normal vector, because outward normal surface area always. This E bar is also, in the case of positive charge, it is radially towards or radially away. Therefore, in such case, ds bar and E bar are parallel. They are parallel. In supposing if you take this as a negative charge, then what you find is that these vectors become anti-parallel. Only two conditions are possible. Two cases are possible here, parallel or anti-parallel. So here E bar parallel to ds bar, I will say theta is 0 degrees is one result that we got. Is it not? Now let us write this integral I will take. What is that? Integral E bar dot ds bar. Now I will write expression for E. Yes. All over. Now let us begin with our simple expression. Now this E, which is intensity at the point P at distance r, then E is equal to 1 by 4 pi epsilon naught. Yes, this is Q. The charge we have taken to be Q. No positive negative signs to be used. We are writing for E, and it is r square. Is what is the intensity, right? Therefore, now let us take this integral E bar dot ds bar. Therefore, I will write it straight away. E times ds times cos 0 degrees. Cos 0 degrees. And this will, now you see this, let us come to this point E again. Now here what symmetry that we have taken as spherical symmetry? Q the charge, imagine to be at the center of the sphere. Therefore now any point P on the Gaussian surface, the distance will be the same r. So for that reason, the intensity, electric intensity due to this point charge will be same at each and every point on the spherical surface, that is the Gaussian surface. Remember, this intensity will be same only in magnitude, because you will find that the direction of E bar is different at different places, normally outwards. So it is not an equal vector, rather same magnitude or any element of surface on this Gaussian surface. Therefore this E, I will take it outside, and this is what is integral ds. Integral ds. Therefore here, what is this ds refers to? A small element of surface area. If we add all such areas, we get surface area of the sphere. Therefore this is what is E times S. E for the intensity at a distance r, and S is the surface area of the sphere. Therefore this is what is Q by S 4 pi epsilon naught r square, expression for the intensity. And what is the S? Sphere, radius r, surface area is, yes, it is 4 pi r square. You remember? All geometries, the different distances, areas, volumes, it should be a common sense for us, at least in second year. Now you will find the result here, right? 4 pi r square, 4 pi r square. So now when I am evaluating this integral, forget about that phi. You don't look at that phi. You let us only look at that phi and this one. Let us not look at this one. What we get is the final result. Therefore now here what you find is that 4 pi and everything getting cancelled. Therefore finally you are getting your result as Q by epsilon naught. In your notebook you write it as one more line. Here I am just finishing it off. This is what is integral, yes, E bar dot ds bar is equal to Q by epsilon naught. Now according to our definition, this integral E bar dot ds bar is nothing but flux. Right? This integral E bar dot ds bar is nothing but flux. Therefore now, what is the result that we got? Yes, the same. Phi is equal to 1 by epsilon naught times, of course here I take it as capital Q, right? Yes, Q by epsilon naught. Here you please look at this Q. What is Q? Don't say it is charge, it is point charge. No, no doubt it is a point charge, but in fact here what is the Q? It is the only charge inside this Gaussian surface. Inside the Gaussian surface it is the only charge. Is it not? Therefore now this is nothing but we can now write our result. Shall we write the result? Yes. The flux enclosed flux through a closed surface. Remember, when we are writing Gauze Law, this closed surface, never say surface when we are using Gauze Law. Alright? So final expression I am now writing, this is what is phi is equal to, yes, 1 by epsilon naught times Q. Q is nothing but the charge which was inside this Gaussian surface. Now shall we call it as a proof? No, in fact it is, we have simply demonstrated from our known concept or known understanding of the field. Now please remember, earlier I have told you, a closed surface I have taken it as a closed surface, I took it as a spherical one. Now somebody may have a doubt. What about if it is some other shape? Maybe asymmetric, some arbitrary surface is taken of arbitrary shape. Then what about the result? Now let us see that one also. Let us see that one also. Now for that, the extension of the same figure you will find. What is the extension of that figure? So earlier we have shown that this is what is the Gaussian surface, a sphere of radius smaller. Hope you can see here. This is, of course, the charge was placed at the center. Or is it necessary? That also we will see. This is a charge at the center. Imagine R is the radius. For this we got this result. Now, remember, I will show these field lines. These are the field lines that we have shown radially outwards like this. Is it not? Supposing now I consider another Gaussian surface of arbitrary shape. This one I call S1, which is a spherical geometry, a surface. Now I consider one more surface, and that is arbitrary. Suppose I consider an arbitrary surface like this. This is an arbitrary surface. Now tell me what will be the result. Now this is the charge, and these are the fields that are emanating from the charge. Therefore what we do is that we extend this line of force, is it not? We extend this line of force. Extend the line of force. What you observe is your good observation. Yes. What is that you observe? Because flux according to us is nothing but the total number of electric field lines through that surface. Now S1, this S2 with the green color is of different shape and different size. Remember, S1, S2, look at those, they are different shapes and also different sizes. But still one thing is same, one thing is common with them, difference of shape and difference of size, yes, but what is that common thing between both S1 and S2? That is what is your observation. You pause the video and look at this. Suppose here I have represented some 1, 2, 3, 4, 5, 6 lines I have shown. So how many field lines are emanating through S1? It is number 6. Now, similarly, when you see for S2 also, when you see for that surface S2 also, remember all these geometries not 2D, they are all 3D geometry. Now through S2 also, what is that number? Number 1, 2, 3, 4, 5, 6, the same. Is it not? Therefore, whatever flux is linked with S1, the same is the flux linked with S2 also. Therefore, now the point comes that when we are imagining a Gaussian surface, a closed surface, enclosing the charge, we get a doubt why we should enclose that charge and why this 3D geometry and all. Wait, we will find very, very good applications. What for this Gauss law is finally, we will find it. Now the point is that whether we are considering a Gaussian surface, a spherical one or a cylindrical one or any arbitrary shape, doesn't matter, we get the same result. Result is the same. But the point is that when we consider such symmetric, like spherical, cylindrical, in all such cases, our mathematics will be simpler and it is convenient, and that is why conveniently all the times, almost all the times, whenever we construct a Gaussian surface, that will be a kind of symmetric 3D geometry, such as, remember, now I am mentioning that, such as, number 1, it can be either spherical or cylindrical or parallelepiped, all such things we will consider, right? One more point. When I have underlined in the statement, there was like net charge enclosed, and also inside net charge is there. Now let us focus our attention onto those terms. Now here comes, you see, supposing in the Gaussian surface, as we did a sphere of radius r, the charge was initially imagined at the center of this sphere. Now the question is that whether this charge is at the center, or supposing this is not, and supposing I take one more Gaussian surface, same kind of suppose a sphere, suppose I consider charge here, not at the center, what difference it makes? No difference. 1, 2, 3, 4, 5, 6. Earlier, whatever the field lines that you have shown, the same field lines I will show here. If it's the same 1, 2, 3, 4, 5, 6, same number is there. That is, so don't be under a misconception that whenever we are constructing Gaussian surface, no doubt symmetry, mathematical conveniences, we imagine the charge to be at the geometric center of our geometry, but it need not be. The charge can be anywhere in the Gaussian surface, it doesn't matter. Got one point. Now, let us see what do we mean by net charge, this understanding of net charge. So it is one after the other. First we have the statement, then we have in one way demonstrated that Gauze law for a simple case of a spherical geometry, spherical symmetry, which we call Gaussian surface. Now here let me take, supposing this is some Gaussian surface of arbitrary shape, and here it has not a single charge. Rather this time I will write it has a charge, say plus q1, and this is enclosing another charge here somewhere over here. Supposing this is a charge minus q2 and this is the charge another one plus q3, so on. Let it be any number. So now it has enclosed not a single charge, rather there are 2, 3 or a number of charges. See here. And of course again it can be either positive or negative. Positive or negative. Now here what do we mean by net charge? Yes. Q net is nothing but, of course, the additive property. Remember, additive property, whenever we are adding the charges along with the sign, we will add that is what is Q1 plus Q2 plus Q3. And of course here, if this is negative sign, we will use the negative Q1, yes, minus Q2 plus Q3, like that. So remember, this is what is the meaning of net charge enclosed by the surface. Now when we are writing the Gauss law, we set Q net inside the surface. Now a rational doubt arises for any at least some of the students, that what about the charges which are outside? Because we have a kind of closer surface, the Gaussian surface, enclosing the charge. Supposing if there are some charges outside the Gaussian surface, supposing for that I will take to demonstrate, here is a charge Q1, suppose it is positive. And I have a charge which is Q2, supposing it is negative charge, and that charge is outside. Now, the point is, first let me show the Gauss law expression. Gauss law says that integral E bar dot ds bar is 1 by epsilon naught times sigma Qi. In such case, remember here, this Q is only the inside charge, whereas this capital E refers to the field due to both inside and outside charges. Remember, this Q on your RHS refers to only the charges which are enclosed by the Gaussian surface, whereas this E in your left hand side, yes, remember this E represents the net intensity due to both inside charges and outside charges. You make it as an important note whenever even you are writing board examination also. In this expression, E refers to net intensity due to both inside and outside charges, whereas Q is only the charge present inside the Gaussian surface. Now, the question is that why this Q2 does not contribute? Is it not outside charge? Let us see that outside charge case as well now. Now let us discuss about the charges that are outside the Gaussian surface. Now this is a charge I have considered outside the Gaussian surface. Supposing this is a positive charge. See, positive charge is a kind of convention that I am taking, need not be always positive as well. Now here, let us draw the flux, that is the field lines emanating from this positive charge. Once again, as you can see, the positive charge, outward flux, what we say, divergent flux. Supposing this is what I have shown as the flux. Of course, now directions you can take. The flux through this surface I have shown. Now this is where the area, I will mark it, this is where the field lines are entering the surface. Yesterday we have to remember that S bar parallel to E bar, S bar anti-parallel to E bar, 0 degrees, 180 degrees. 0 degrees means outward flux, 180 degrees means inward flux, or anything less than 90 it is outward flux, anything greater than 90 inward flux that we have shown yesterday, right? So in such case, now here this is the flux which is entering, and then I extrapolate these field lines. Supposing if I extrapolate these lines, yes, extrapolate this line, yes, and extrapolate this line as well. What you observe, boys? Yes, friends, what is that you observe? Now here one more time I will give a shade of this region, right? You call this as S1 part of the Gaussian surface, and this is what is S2 part of the Gaussian surface. Now what you find here is that, yes, at S1, the flux is, suppose phi1 is equal to minus phi. Why minus phi? Yes, it is what is our understanding. Inward flux happens to be negative, outward flux happens to be positive. So this is at S1, that is flux entering, and now what about at S2? Yes, you can see S2 you will find it as the outward flux, therefore this phi2 is a positive number. Therefore, now what is the net flux linked with the Gaussian surface? Net flux for our Gaussian surface. Yes, it is, yes, phi1 plus phi2. Yes, now you will find this as 0. Now, what is that we observe? If at all there are charges outside the Gaussian surface, they does not contribute to the flux, to the net flux for that Gaussian surface, linked with the Gaussian surface. That is why we have taken in the definition or the statement we have studied as only QR. Does not mean that no outside charges are present. Outside charges may be present, but they have no effect whatsoever on the flux linked with that Gaussian surface. But remember our statement one more time, that that phi on the LHS was, of course, that Q was that Q here refers to inside, but RHS, the LHS, you have that field vector E bar. But E bar is not just due to inside charges, it is due to both inside charges and outside charges. Therefore, outside charges contribute to capital E bar, but it does not contribute to phi is an important thing. And that what makes this Gauss law a very, very beautiful one. Because though outside charges are there, we need not consider their flux. But their contribution for the field, we will have it in our results. So that is what is the beauty of our Gauss law. So now if the entire things you summation, you just make a summary. First the statement, afterwards we have given that mathematical statement. If for board examination, state and prove, sometimes maybe a question like that may be nonsensical but may be given. In that case, we have shown that case of a spherical symmetry that we have considered for the case of point charge. We have given that as a simple demonstration. And after that, we have said what is meant by net inside charge. And also we have discussed about the charges which are present outside the Gaussian surface. Now, this is all about Gauss law statement and all for board examination. Now, keeping that aside, first let us keep it aside. Now let us start speaking more things about this expression and all. In this expression, phi is equal to 1 by epsilon naught qi. What is that you observe? You observe that flux depends. That flux depends only on the inside charge and not on the outside charge. And remember, this expression does not have any parameter whatsoever with respect to size. There is no parameter with respect to size. So what does it mean? Flux enclosed. I'll make two statements here, or one statement only. In that one statement, you will find out other things as well. Because at times English, when we use that only, and it makes a big difference. Therefore, the flux, I'm talking about the flux, of course, through closed surface. Flux through closed surface. Now let me write some of the parameters and let us comment on its effect. First one, the charge. Charge means, of course, enclosed. Yes, it depends upon the charge enclosed. For positive charge, we will find outward flux, and negative charge will find inward flux. And then whether it depends upon shape of the enclosure. Answer is no. Whether it depends on size of the enclosure. Answer is no. Where you will find that no question of anything regarding shape or size. Now one more time. Does it depend on medium? Does it depend on medium? Because you remember, whenever we are making any such statements or any such explanation, we are always, one thing is understood, that we are considering the case of the charge in a charge in vacuum that we have considered at our study. It's understood. Unless and otherwise a teacher says that yes, this is what is the medium, then only we will consider that medium. Now remember, does medium has any impact? Medium has any impact? I leave it to you as a question. Actually, I want to leave you as a question. Because you remember, we said about the force. We said about the force in air and force in the medium. Remember that? Force in the medium and force in the air. We said F in the medium is, yes, F in air by capital K was there. Is it not? This was our result when we discussed about all the Coulombic force. Force between charges in the medium is lesser as compared to the force between the charges in air. It's because K is always greater than 1, we said, right? Now remember, if it is field as well, because in Gauss Law, which expression you have integral E bar you have, right? E bar is nothing but a force vector, because that is nothing but E is equal to F by Q, not our definition. Therefore, once again, E in the medium is equal to E in air upon K. E in the medium is equal to E in the air upon K. Therefore, now if we write Gauss Law. Gauss Law, now we hear the statement as integral E bar dot ds bar equal to, yes, Q, of course Q with all that understood that inside net everything is there. Okay, but still let me write sigma Qi by epsilon naught what you observe here. This is integral E, I will use an adjective, this is in A. This is in A. Now let me write the Gauss Law, the medium. Gauss Law in a medium. Let us write. Therefore now according to our this discussion, it depends upon, yes, the charge enclosed, and it depends on the medium also. Only two aspects, charge and medium. Charge means inside charge, medium, which is enclosed by the Gaussian surface, of course, not depending upon the shape or size, was our result. Now let us write Gauss Law in a medium. Gauss Law in a medium, if I write integral, yes, Em bar dot ds bar is sigma Qi by epsilon naught. And what is this definition of Em earlier we have shown? Therefore this is integral 1 by k times E bar dot ds bar. This E of course referring to the field in the case of A is sigma times Qi by epsilon naught. Qi by epsilon naught. This will be in medium. This will be in medium. Is it not? Maybe sometimes we are given the case of other medium and also to find the flux or expression for Gauss law, and that is we have shown here. Now we are talking about the charge, considering only one charge and Gaussian surface and all. But remember, why this Gauss law is all? Why this Gauss law at all? As I have told you, now this law, though it is nothing but another form of Coulomb's force only. Definitely one can say that this is another form of Coulombic force only. Now therefore, Coulombic force has a limitation. As I have told you, for discrete charges it is very good at working out with Coulombic force, but for the case of continuous charges, though it can be applicable, but the process is a bit laborious and all. But here comes the Gauss law. Using Gauss law, now we can find this electric field for any given distribution of charge, whether it is a discrete or continuous charge distribution, right? And one such example I would like to show you in this session. So let us now use Gauss law to find the electric field intensity. That is again a three-step process. So first I will explain that three-step process, and the same 1, 2, 3 steps we will apply for any given distribution of charge. Interesting. I will do 2 1 jar 2 and I will ask you 3 1 jar 4 1 jar. Right? A very good game for you in the lockdown period. Let us do that. Yeah, wanted to do that Gauss law application, but it's already about 50 minutes of time. It takes another 20 to half an hour if I continue with the topic. So we'll have our discussion and application of Gauss law in our next class. Prepare well, be happy, stay home healthy. Good day, boys.